A limit is the output value that a function approaches as the input value gets closer and closer to a specific value. In this video, I'll teach you how to find limits graphically. First, you must familiarize yourself with limit notation. This expression would be read, the limit as x approaches 4 of f of x is equal to 3. It means that as the input values approach 4 from the left or from the right, the output values of f approach 3. This can happen in a variety of ways, but here's another example. It doesn't have to be linear. As the input values approach 4, the output values approach 3, both from the left and from the right. The limit as x approaches infinity of f of x means the output value that f of x is approaching as the input values increase without bound. For this function, the limit as x approaches infinity of f of x is equal to -2, because we can see that as the input values increase without bound, the output values approach a value of -2. The limit as x approaches negative infinity of f of x means the output value that f of x approaches as the input values decrease without bound. In this case, as the input values decrease without bound, the output values increase without bound. So the limit as x approaches negative infinity of f of x is equal to positive infinity. Or in calculus, when the limit is infinity or negative infinity, we also can say that the limit does not exist. And we abbreviate that dne. It makes sense that the limit does not exist in this case because as the input values decrease without bound, the output values do not approach any specific value. By default, when we talk about the limit as x approaches a number like this, we mean the two-sided limit as x approaches the number from the left and from the right. But we can also talk about one-sided limits. This negative sign superscript means we are talking about the limit as x approaches 1 from the left of f of x. So we are talking about the output value that f of x is approaching as we approach an input value of 1 from the left. In this case, the limit as x approaches 1 from the left is 2 because we are approaching an output value of 2. Notice it does not matter that there is an open circle right here at 2. All that matters is that we are approaching an output value of 2 as we get closer and closer to 1 from the left. This plus sign superscript means we are talking about the limit as x approaches 1 from the right of f of x. In other words, we are now speaking of the output value that we are approaching as we get closer and closer to the input value of 1, but this time from the right. The limit as x approaches 1 from the right of f of x is -1, because as the input values get closer and closer to 1 from the right, the output value gets closer and closer to -1. Again, it does not matter what's happening at 1. All that matters is what's happening as we approach 1 from the right. Here comes a key concept that you need to understand about limits. This overall two-sided limit as x approaches 1 of f of x does not exist. For the overall two-sided limit to exist as x approaches c, the limit from the left must equal the limit from the right. In other words, the function must be approaching the same output value from the left and from the right of the input value in question. That means anytime you see a jump discontinuity, you know the limit does not exist at that input value. Here come 3 common situations where the limit does not exist. We already spoke about the first one, where there is a jump discontinuity. The limit does not exist at C. Also, if there's a vertical asymptote at C, the limit as x approaches c does not exist. Let me be clear. Even though I just told you that the limit exists if and only if the limit from the left is equal to the limit from the right, that does not include this situation. Even though the limit from the left is infinity and the limit from the right is also infinity, that just means that the limit does not exist on the left and the limit does not exist on the right. So surely the overall limit does not exist. It will not surprise you that the overall limit does not exist if the function approaches a specific value from one side and an asymptote from the other side. Once students learn about limits, they often have a hard time keeping straight the difference between this concept and this concept. This expression on the left means the value of f of x at x equals 2. In this case, the value of f of x at x equals 2 is given by the closed circle and never the open circle. So f at 2 is equal to 3. By contrast, the limit as x approaches 2 of f of x is the value that f of x approaches. It is not the value at 2, that's what this is. It's the value that f of x approaches as we get closer and closer to an input value of 2 from the left and from the right. In this case, as the input values get closer and closer to 2 from the left and from the right, the output values get closer and closer to 1. So this limit is equal to 1. For limits, it does not matter what's happening right at 2. It does not matter that there's an open circle here. It does not matter that there's a closed circle floating around up here. The output value is approaching 1 from the left and from the right, so the limit is 1. Let's evaluate each one of these expressions. The limit as x approaches c from the left is equal to 2. The output values approach 2 as we get closer to c from the left. The limit as x approaches c from the right is also equal to 2. The output values again get closer and closer to 2 as we approach c from the right. Since the left-sided limit is equal to 2 and the right-sided limit is also equal to 2, the overall limit exists and it is equal to 2. This expression f at c means the value of f at c, and that is also 2. The green picture is almost the same, so I'm going to do it very quickly. The limit as x approaches c from the left is 2. From the left, we are approaching an output value of 2. The limit from the right is also 2. We are still approaching an output value of 2. It does not matter that there is an open circle at c. Limits don't care what's happening at c. Since the left-sided limit and the right-sided limit are both 2, the overall limit is also equal to 2. However, f at c is undefined. F at c means the value of f right at c. There's an open circle here, and there's no closed circle anywhere else to give us the value of f at c. So we say f at c is undefined. Notice we do not say f at c does not exist. Save the expression does not exist for limits. Pause the video for a moment and evaluate these 4 expressions by yourself. I'm going to assume that you did that. So the limit as x approaches c from the left is 2. As the input values approach c from the left, the output values get closer and closer to 2. The limit as x approaches c from the right of f of x is also 2. As the input values get closer to c from the right, the output values again get closer to 2. Because the left-sided limit and the right-sided limit are both equal to 2, automatically the overall limit is equal to 2. What about f at c? The value of f at c is given by the closed circle. So that's going to equal 3. Pause the video again. Try to do all 8 of these expressions. So the limit as x approaches c from the left of f of x is equal to 2. From the left, we are approaching an output value of 2. The limit as x approaches c from the right of f of x is 3. Because the left-sided limit and the right-sided limit are not the same value, the overall limit does not exist. Don't put an equal sign here. This is wrong. If you write a limit and then you say equals dne, you're going to lose a point. So just don't put anything and just put dne. How about the value of f right at c? All I see are open circles. So that means f at c is not defined. Don't say dne, that's for limits. We say f at c is undefined. Switching to the purple graph, the limit as x approaches c from the left is 2. The limit as x approaches c from the right is 3. Again, the overall limit as x approaches c does not exist because the left-sided limit and the right-sided limit are not the same. What about f at c? F at c is equal to 3. When there's a closed circle, the closed circle tells you the value of the function at c. Pause the video and try to evaluate these 5 expressions on your own. Number 1 says the limit as x approaches -3 from the right of f of x. Here is the input value of -3 right here. As we approach this input value from the left, we stay at an output value of 3. So that's the limit. Number 2 says the limit as x approaches -3 from the left of f of x. So here's that input value of -3. As we approach this input value from the left, we are approaching an output value of -1. So that is the limit. Number 3 does not have a plus or a minus. So this is the overall two-sided limit as x approaches 4 of f of x. Here is the input value of 4. For this limit to exist, f of x must approach the same output value from the left and from the right. And indeed, as we approach this input value from the left, f of x approaches the output value of -3. And as we approach this same input value from the right, f of x again approaches this output value of -3. So the overall limit is -3. Number 4 says the limit as x approaches 0 of f of x. Of course, here is the input value of 0. Again, this is the two-sided limit as x approaches 0 from the left and from the right. So for this limit to exist, f of x must be approaching the same output value from both sides of this input value. Do not be alarmed by the fact that there is no dot or circle right at 0. That's okay. We can still talk about approaching this input value from the left and from the right. I think I'll even make it kind of zigzagged like this. Either way, as f of x approaches 0 from the left or from the right, it is approaching this output value that's right here. I think I'll put a little blue dot here. We're approaching the output value of 3 from the left or from the right. It does not matter that there's no dot there. Sometimes that disturbs my children. Ooh, that's skinny. This last expression means the value of f at 4. So here is our input value of 4. And the value of f will be given by the closed circle, not the open circle. So f at 4 is 1. Here are a few examples involving horizontal asymptotes. the limit as x approaches negative infinity of f of x is equal to whatever this output value is. Let's go ahead and put an x and y axis on it, so we can say the limit as x approaches negative infinity of f of x is equal to 2. As the input values decrease without bound, the output values approach the asymptote of 2. What about the limit as x approaches positive infinity of f of x? Well, as the input values increase without bound, the output values decrease without bound. They are falling and falling and falling. So we can say that this limit is equal to negative infinity, or it's probably safer to say that the limit does not exist. That way you don't have to be correct on the negative infinity versus positive infinity. Either way, D and E is the right answer. One more time, let me emphasize that you never put an equal sign in front of D and E. This green function is oscillating between negative and positive as it goes to the left and the right. What is the limit of f of x as x approaches negative infinity? Well, as the input values decrease without bound, f of x oscillates between positive 1 and negative 1 forever. Because the input values oscillate between two different values, never approaching a single value, this limit does not exist. Do not put an equal sign here. But what about the limit as x approaches positive infinity of f of x? As the input values increase without bound, even though f of x continues to oscillate between positive and negative, the output values are approaching a specific input value of 0. So that will be the limit. It does not matter that the output values continue to oscillate positive, negative, positive, negative. They are getting closer and closer to 0. So the limit does exist, and that limit is 0. Let's do a few problems involving vertical asymptotes. What is the limit as x approaches c from the left of f of x? As the input values approach c from the left, the output values increase without bound. So this left-sided limit is positive infinity. Similarly, as x approaches c from the right, the output value approaches positive infinity. So the limit as x approaches c from the right of f of x is also equal to positive infinity. In both cases, I encourage you to simply put D and E, so you don't have to choose between positive infinity or negative infinity. What is the overall limit as x approaches c of f of x? Well, that simply does not exist. Don't even put positive infinity, even though from the left it's positive infinity, and as we approach c from the right, the limit is positive infinity. That just means the limit on the left and the limit on the right did not exist. So, of course, the overall limit does not exist. Do not put an equal sign here. What about f at c? Right at c, we have an asymptote. F of x never touches the asymptote, so f at c is undefined. Notice that I don't say does not exist. Save D and E for limits. Switching to the blue function, the limit as x approaches c from the left of f of x is like this. As we approach c from the left, the output values increase without bound, so the limit is positive infinity. How about as we approach c from the right? Well, as the input values approach c from the right, the output values approach, well, whatever this output value is. Let's call it 2. How about the overall limit as x approaches c? Well, since the limit from the left is infinity, we already know that the overall limit does not exist. For the overall limit to exist, the left-sided limit and the right-sided limit must both exist, so no infinities, and they have to both be the same number. The value of f at c is still undefined. We see the open circle here at c and nothing else. For the last few problems, we will sketch the graph of one function f that satisfies all of these conditions. So the function that we are going to graph is going to be a piecewise function, but it must pass the vertical line test because it's really one function. A says the limit as x approaches negative infinity of f of x is equal to negative 1. The only way the limit as x approaches negative infinity will equal negative 1 is if we have a horizontal asymptote at y equals negative 1. As you can see, I've started off my graph of f of x with a horizontal asymptote at y equals negative 1. So indeed, the limit as x approaches negative infinity of f of x is negative 1. Part B says the limit as x approaches negative 2 does not exist, but the limit as x approaches negative 2 from the right does exist. And also, f at negative 2 is equal to 0. Let's break this down. This first part that says the limit as x approaches negative 2 does not exist means one of two things. If the overall limit does not exist, that means there's either a jump or an asymptote at x equals negative 2. However, the next part says the one-sided limit as x approaches negative 2 from the right does exist. That means there can be no asymptote from the right. So the easiest thing to do is just to let there be a jump at x equals negative 2. I'm also keeping in mind that the value of f at negative 2 is to be 0. So I might as well go ahead and put the closed circle showing the value of f at negative 2 is 0. And that will also allow me to create this jump. Because as I continue what I had before, that's a little skinnier than I wanted it. I'm going to continue this piece of the graph on its merry way, but I'm going to put an open circle right here. And then we have the jump. So this satisfies all three conditions. The limit as x approaches negative 2, the overall limit, does not exist because of the jump. The limit as x approaches negative 2 from the right does exist because from the right we are approaching a specific value of 0. And f at negative 2 does equal 0 because of the open circle. Part C says the limit as x approaches negative 1 from the left is equal to the value of the function at negative 1. By the way, this statement implies that both of these things exist. They can't equal each other if either one of them does not exist. If I simply put a closed circle here at negative 1, suddenly f at negative 1 exists. And specifically, it is a value of 0. By connecting this up in this way, the limit as x approaches negative 1 from the left is also 0. In addition, however, Part C says that the overall two-sided limit as x approaches negative 1 does not exist. So I can either throw in an asymptote or I can just make a jump. So I think I'm just going to keep it simple and put a jump right in here, which makes the overall limit as x approaches negative 1 not exist. Part D says the overall two-sided limit as x approaches 0 exists, but f at 0 does not exist. Well, for the limit to exist from the left and the right, the function must be approaching the same output value from both sides. However, since f at 0 is not defined, we need to leave an open circle. So we just need to draw something that looks like this. So picking up where we left off, I'm just going to put an open circle at 0 and sort of connect this up. And that's it. So the overall limit as x approaches 0 exists because we are approaching the same value from the left and the right. However, f at 0 does not exist because of the open circle. Part E says the limit as x approaches 2 exists. So right away, that means that we are approaching the same value from the left and from the right. It also says that f at 2 is defined, so I'm tempted to fill this in. However, it also says that the limit does not equal to the value of f at 2. So if f at 2 exists, but it's not the same as the limit, that means we have a closed circle somewhere other than where the lines are approaching. So I need to draw this type of piece in right here. So we're talking about as x approaches 2. So as x approaches 2, I just need an open circle and some other value as we come in from the left and from the right. Part F says that the limit as x approaches 3 from the left is equal to 1. So the left-sided limit exists, so we know it's got to be approaching the specific value of 1. The limit as x approaches 3 from the right is equal to negative 2. So on the left, it's coming in at 1, but from the right, it's coming in at negative 2. It does not say what's happening at 3, so we can choose whether we want to just leave it undefined or if we want to make one of these a closed circle. That does not matter. So far, I've drawn this blue piece so that the limit as x approaches 3 from the right is 1. We are here at an output value of 1. So I've done this first part. Now I need to draw the part so that the limit as x approaches 3 from the right is negative 2. Okay, negative 2 is down here. These cannot both be closed circles because that would violate the vertical line test. But here we are approaching 3 from the right at a limit of negative 2. And finally, the limit as x approaches infinity of f of x is equal to 2. This means another horizontal asymptote, this time at y equals 2. So picking up where we left off, we just need to make sure that f of x approaches this horizontal asymptote at y equals 2. There's more than one right way to draw the graph of f of x, but this is one. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.